had two problems in preparing this talk. One was simply my own poor planning, that I ended up with a lack of preparation time due to other things. And the other was that, of course, there are many of us due to speak in this meeting who come from the same broad background in science, and there was therefore a big issue of whether I would simply be duplicating what other people had said. And of course, I didn't know if I'd have the opportunity to speak before them or after them. And reading their abstracts didn't necessarily tell me what they were going to say. So I had two effects. One was I was worried about the amount of content. Would there be too little to say because it would have been said by other people? Or on the other hand, would I have too much to say because I would want to comment on what they had said? And indeed, I think almost every slide that's been shown this morning prompted a comment that I would have liked to make, even if I wasn't critical of its content. The other effect has been on style. When I was in university management, I had to attend a large number of inaugural lectures by professors in various disciplines, and I became aware of the fact that scientists like to prepare a series of slides and talk around them. They don't have a text, whereas in most areas of the humanities, there is a very carefully formulated text, a script, which is absolutely rigidly adhered to, because any change in the text will give a different nuance. And scientists and mathematicians don't care about nuance. In fact, they try to avoid it as much as possible. But if you're in the humanities, you want to exploit nuance, to have these differential interpretations and so on. So that led to another problem, that this is almost a sort of humanities type talk given by a scientist, because it's about methodology and some issues connected with philosophy rather than being straight science. And so what I've ended up doing is, in a sense, a horrible mixture of these methodologies by having some prepared notes and headlines which I'm going to talk around, but not having a prepared full text. First thing I want to say is, why did I choose to put the word bounds and not limits in the title? And I have to admit this is because of my original training as a mathematician, thinking of the mathematical idea of a limit, that first of all, limits can be infinite. And I wanted to stress finiteness. Secondly, I wanted to think in some cases about limits exactly as mathematics thinks of them, some of which are reasonably understood, and indeed my first example was actually raised by John Barrow in answer to the question at the end of his talk, which is the example of the way in which general relativity limits to Newton's theory, which we, at least, even if we've only done a first course in relativity, think we understand, because we know that the weak field limit is used to deduce the fact that the constant in Einstein's equations is related to Newton's constant. It's 8 pi g over c to the fourth, in the usual way of writing it. But in fact, that limitation is not quite what the Kuhnian paradigm shift would suggest. As John pointed out, the progression of our understanding of mechanics can be understood as an evolution in which some elements of previous structures are discarded and others are generalized, and that earlier theories can be obtained as a limit of later ones, Newtonian gravity as a limit of general relativity. But there is an alternative interpretation of these shifts, which is that the later theory provides a natural understanding of the earlier one, even if the earlier one is not a limit. For example, Aristotelian mechanics, in which air resistance and other friction was not known, led to the idea that force was required to sustain motion. From a proper understanding of Newton's ideas, we know that force is required to change motion, and the reason that objects, if they're moving, slow down and stop, is not because they lack a force sustaining the motion, it's because there are other forces acting that make them change their state of motion. So the change in paradigm can be can give a limit to the old theory, or it can give an deeper understanding of the old theory, even though it's a completely different understanding. The second thing I wanted to say about it is that although many calculations in cosmology and astrophysics are done with Newtonian gravity, the use of Newtonian gravity is only valid in certain regimes, and one has to be very careful. This is where you hit the issue of bounds that are bounds in principle, that Newtonian theory in fact only gives a limit of one of the 10 relativistic equations, in effect. The other 9 are not necessarily solved in Newtonian analogues. And the result of that is that there are solutions of Newtonian theory which have no general relativistic analogue. The second point is that the boundary conditions are problematic, essentially for the reason that John alluded to, that information is transferred instantaneously in Newtonian theory, so if you change the boundary condition, there's an instantaneous effect on the local conditions. The third problem is related to that, which is there's no unique equation for the time development of the Newtonian potential. And finally, there's the problem of the gauge dependence of the Newtonian limit. What I want to say about all those things is that they are bounds in principle rather than bounds in practice. There are other sorts of limit that are less well understood. For example, the relation between where does the quantum theory limit to a classical theory? And I don't think this is, I mean, it may be that it's well understood, but it's certainly not well understood by me, and I haven't heard a discussion in which it's been explained in a way that I felt was well understood. For example, one might ask if the recent BICEP2 results, assuming they're confirmed by Planck in sometime later this year or early next year, do they help to verify the belief that quantum fluctuations in the early universe, which we can't directly observe, really do give rise to the classical fluctuations that we measure in the cosmic microwave background? I mean, trying to understand that issue, I came across a remark by Padmanabhan in one of his books that one should regard the carryover of the quantum fluctuations to the classical regime as a definition rather than something which we scientifically understood. Perhaps the most awkward of these sort of limits questions is how we can, by putting in more and more detailed information, build up what people think of as complex phenomena or emergent phenomena. How can we, by understanding a single grain of sand, understand the way that if you pile up sand, you eventually cause an avalanche of it? We simply don't understand that. Is that a bound in principle or merely a bound in practice? And I don't know the answer to that question. So that's, I'm just getting on, okay. So the second thing about my title, I explained why I want to talk about bounds rather than limits. Why did I say bounds on rather than in physics and cosmology? And actually I'm interested in both, but bounds on physics and cosmology partly tie up with the question of where does physics end? Bernard pointed out that he believes that our understanding of consciousness, our experience of time, should be part of physics. Is that the right way to think about it, or is that a redefinition of what we mean by physics? I mean, for example, if I would ask any physicist in this audience, how can they define what are gravitational phenomena in such a way that I could go and look at something and know immediately whether it was a gravitational phenomenon or an electromagnetic phenomenon? It's actually very hard to set down in any form of words what the difference is between those two, although physicists generally would agree which is which. So what is physics and what is something else? It seems to me a very difficult question. We also know that, I mean, as was alluded to, the issue of theories of everything. We know that theories of everything are not theories of everything. Theories of everything in physics don't set out to cover love, humor, beauty, free will, many of these big questions. If they did, would we be pleased? Or would we be upset that we had a reductionist explanation that might destroy many of the values we thought we had? That, if love was really just a predetermined outcome of a particular assembly of elementary particles and fields, how would we feel about knowing that? Might be very devastating. We might all go and commit suicide. So those are some bounds on physics. There's also the obvious bounds in practice that we've mentioned, the bounds at high energy, that prevent us knowing as much as we would like to about elementary particles of very high mass, prevent us knowing as much as we would like to about the early universe, because we can't do terrestrial experiments beyond a certain energy. And one could probably do some sums that estimated the largest possible energy you could hope to get to by terrestrial experiments with any reasonable acceleration of particles and so on. At any time, of course, there is a maximum energy we can get to, and that does change with time, but it's hard to believe that it could increase without bound. In fact, in the case of the early universe, we probably get to what Salam, in a very nice little lecture in the Dirac lecture series, referred to as the speculative era, by analogy with the hadron era and radiation era and so on. The second point, of course, about bounds is, as well as the bounds of high energy, there are bounds of large distance, which is the other side of Bernard's Ouroboros. John very kindly showed a picture about horizons, which helped me a little bit. I want to just show a couple of pictures related to that. And this is where I really wish I'd had more time to prepare some slides, but let's see if this will work. So, okay. If we had the old Cockney Mang model, one of the problems in the origin of inflation, do I need this? I'm not loud enough? Never mind. It's a bit like, I had a friend who worked for an airline in New York, which served mainly the southern states, and she once heard the woman on the next desk saying to a customer, "Sir, if you can talk faster, I can listen faster." So one of the problems that prompted the theory of inflation was this problem of horizons, that if we look in different directions in the model of the universe pre-inflation, you see regions that appear to be very similar but have had no causal contact from the time of the Big Bang onwards. It's interesting that that motivation is really not mentioned these days, along with the other two motivations for inflation. They're really not discussed very much, because the thing that convinces everybody that inflation is a good theory is, in fact, as John mentioned, the power spectrum of the microwave background, and perhaps more recently the BICEP 2 result if confirmed. So it's the fluctuation spectrum that is really important, and these original motivations are not. So I want to show this, which is a diagram of what you get with inflation, and just point out that inflation doesn't entirely solve the horizon problem, because this point here is influenced by the past null cone, and this point influenced by its past null cone, and they now intersect in a very large area. So most of the data that affects this point is the same as the data that affect that point, but of course critically not all of it. So in an absolute sense, and in principle sense, something could happen here that affects what happens there and does not affect what happens at another point, And in that sense, inflation does not solve the horizon problem. It only mitigates it by saying that the amount of common data between separated points is a large fraction of the total, at least in the standard pictures. And of course, if you had a totally different kind of universe down here from the one assumed by inflation, this could get even worse. I don't know if I need to keep this, but I'll keep it anyway. Now, the next thing I wanted to say was I talked a bit about bounds on physics. I want to talk a little bit about bounds. Am I okay with it? Okay. I talk about bounds within physics, and there are the computational bounds or analytical bounds on what we can understand in complexity, which John has mentioned. There's a nice remark of Bondi's in his well-known Cosmology book from the 50s originally, that complexity is a feature of phenomena on our scale only. In other words, in Bernard's Ouroboros, we think we understand perfectly what's happening at the top of his picture. It's only at the bottom that we don't understand. It's a bit like the statement, Michael Owen Robinson once said that we understand everything about the first 3 minutes of the universe's life perfectly. It's only the remaining 10 to the 10th years that are a little mysterious. So, on the human scale, things are complex. Should we be worried that our microscopic and macroscopic theories that we rely on so heavily are actually too simple? Ought they to be as complex as our understanding of what happens on our scale? The sort of things we can't model are thunderstorms. John mentioned climate change models. Another one which interests me, and I have no deep understanding of it because it's not a subject I've worked on, is formation of galaxies and stars, which is a messy astrophysical process, but somewhere in there must be a link with highly nonlinear physics of black holes, because there is apparently a definite correlation between the mass of a central black hole in a galaxy and the overall size and other parameters of the galaxy, even though the black hole is a tiny fraction of the total mass and an even smaller fraction of the total physical size. There are explanations of this. For example, it could be due to the way in which jets produced by the central black hole, sending material out very large distances at high energies into space, affect the star formation by affecting the temperature of the surrounding gas cloud, which if you heat up the gas cloud, it makes it more difficult to form stars because it can hold itself up against gravity a bit more. So there are, hand-wavy explanations of why this might be true, but I don't think anybody yet has a detailed simulation that really covers the whole field. And the problems come from the fact that simulations need very large dynamic range. So it's back to the emergence issues. And here I take issue with George Ellis, at least with what I understood him to be saying in some of his writings, that he seems to be saying that there really are new phenomena on different scales as the scale changes, and in a sense, therefore, reductionism is wrong, that you can't explain everything by these fundamental microscopic or macroscopic theories. That may just show that we can't compute well enough, not that the actual phenomena all depend on the properties of atoms or fundamental particles or on the properties, say, of fields on the very large scale. It seems to me George Ellis's approach, if I've understood it correctly, and I'm not sure I'm speaking for him correctly, seems to me to be noting what is clearly a bound in practice, that's to say the computational limits of what we can actually simulate, and elevating it to a bound in principle, saying that we can't hope to understand these complex phenomena on the basis of our understanding of microphysics and so on. The other thing I wanted to comment on is on boundaries within physics, places where two theories meet. I've mentioned already the quantum and classical transition, and obviously that leads on to a question about domains of applicability. If you wanted to judge the flight of a ball in, or if you wanted to work out the flight of a ball in some team game, say football or cricket, you'd be an idiot to try and do it using general relativity. Newton's theory is perfectly good enough for that purpose. On the other hand, if you wanted to be sure that your GPS system in your sat-nav in your car was going to end you up in the right place, particularly if you wanted to get very accurate, as some people do, you would need to use general relativity. And Newton's theory simply wouldn't give you the right answer. You would be turning left into your neighbour's garden instead of the next road. One particular aspect of that, which a former student of mine worked on, Dan Cox, was to ask, we usually treat sources of gravitational radiation in an approximation which assumes the universe is asymptotically flat and the body or the bodies that are producing the radiation are isolated. One can ask, when is that a good approximation? Where do you have to draw the boundary? In other words, as he put it in the title, how far is infinity in this circumstance? And it turns out to be quite interesting to work this through. What happens is that a diffuse, non-centralized mass distribution gives real problems of this kind. It's very hard to see that there's a clear-cut point at which you can cut off and say, well, that's the isolated system, and outside that we can pretend that it's asymptotically flat, even if we know it isn't. And that boundary turns out to be all right for stars, but not for their planetary systems, for example. If you take the solar system, it's very hard to draw a boundary at which you go over from understanding the outer reaches of the solar system into just being interstellar space. It's equally difficult for galaxies and groups of galaxies, in that case partly because we just don't know what there is in the spaces between them in full detail. We think we know there's dark matter and dark energy, but we don't know enough. On the other hand, it does seem that the asymptotically flat treatment is good enough for stellar size sources of gravitational waves and for active galactic nuclei as a source, or compact objects of that sort of scale. One can, of course, talk about various general issues in the theory of science. I notice in Michael Heller's book with George Coyne, they give what they say are myths, which are things which people assume but which you can't, in a sense, prove. One of them being a myth of value. I mean, that you attach values to things, but you don't have any, in a sense, these just come from some legendary background. I mean, to me, for some reason, Marxism came up earlier in the discussion. And it always seemed to me that one of the problems of Marxism was, even if their account of the evolution of economics and politics was correct, it didn't tell you why you should try to help it along rather than try to slow it down, because that was essentially a value question. And somehow it seemed to place an implicit value on assisting the progress of technology and the dictatorship of the proletariat rather than opposing it. Somehow there was a missing link there of thinking about what the value was. The same thing applies with conventionalist approaches in physics, where you say any theory in physics which will give you the same predictions can be thought of as being of equal value. So you might think of, in the case of special relativity, we know that you can just write down the Lorentz equations and you can interpret them as telling you that distances and times really change if you are moving relative to an ether. That there really is an ether, it's motion within that that causes these effects. The equations, of course, are exactly the same. So it produces exactly the same results. Are those two theories of equal value? Well, most of us would say no, for various reasons. We might say, for instance, that special relativity leads to general relativity, whereas the Lorentz theory doesn't allow you to accommodate gravity. But in some sense, there's an aesthetic question here. And it's like the questions that arise if you ask, why is one theory better than another? And you answer, because it's simpler. But what do you define to be simpler? I mean, simplicity is, to some extent, in the eye of the beholder. We do accept, of course, a view of rationality. We somehow believe the universe is rational, which is the main question that the book by Michael and George Coyne addresses. We have no, I mean, there's a circularity in attempting to prove that. Inevitably, you can't prove that the universe is rational by a rational argument, because that assumes that a rational argument makes sense. You also assume in many physics aspects that the universe is uniform, which is, of course, the cosmological hypothesis, I think as was mentioned in the earlier talks. Another big issue is whether theory is the same thing as reality. And here I would be worried about Bernard's comment that, I think it was Bernard, was talking about mathematics, the relation between mathematics and physics. I mean, Tegmark has recently published a book in which he says that, the universe is mathematics, or, the mathematical universe. The whole of the universe is just exactly mathematics. There's nothing independent about mathematics. Now, I'm not sure how this would fit with Bernard's idea that consciousness should be part of physics. Does this mean that our understanding of mathematics is determined by physics? Whereas most of us, I think, take the opposite view, that our understanding of physics comes from mathematics, and the mathematics arises from, our brains in some way. So I don't know, I don't have an answer to that, but I think our view that somehow we can identify theory and reality goes back to our early training in physics, where, we do experiments on Newtonian mechanics as if what we were measuring really were force and acceleration and all these things. We don't see the fact that there is a link between what we interpret these experiments as showing and the actual experiment itself, which depends on some theoretical constructs. I think that's true for both elementary mechanics and elementary electromagnetism. If we do make that identification between reality and theory, we then hit some problems. First of all, we must believe in some sort of Platonic idealization, because it's obvious our theories don't provide a comprehensive description of all aspects of the world. Secondly, the need to conform to direct reality is not always a helpful restriction on theories. And I was interested that we discussed in the earlier talks the issues about falsification and Popper's ideas. And there's lots of reasons why that's fallen out of favour. One is that it's very hard to see how it applies to certain kinds of theory or kinds of paradigm. What datum could you imagine that would show that Darwin's theory of evolution is false, as distinct from that the course of evolution is not exactly what we thought it was? What datum could you imagine that would show, let's be more provocative, that the paradigm of inflation was false? I've been worrying about that ever since there was this period when it was thought the overall density was 10% of the critical density, and the inflation theorists then came up with theories of inflation that produced just that. It's a little bit of a worry. There's also, more generally in principle, the issue of the asymmetry between verification and falsification. We have the idea that to verify a theory, we need to do an infinite number of experiments in principle, which clearly, of course, we can't. But we can falsify a theory with just one experiment. Actually, I think that's a mistake, because you don't test a single theory, as I think it was John pointed out. You test a bundle of things, and it's very hard to disentangle the assumptions from the empirical facts. Indeed, it has been said it's a truism that there are no naked, purely observational facts. They're all passed through some theoretical framework before you start to think about them. So data can't be confronted with pure theory. Perhaps in changing theories, we need to have a new theory to hand before we go about rejecting the old. If not, the old one will carry on being believed. And maybe that's connected with Bernard's remarks about belief and the impact of great scientists. Actually, I'm not so sure it's great scientists. It's more a general thing. I mean, and I think, incidentally, that question of belief is why we, assuming most of us here are scientists, have a real problem in dealing with the public media and with the public. That the media tend to ask what scientists believe, and scientists try not to believe. So good scientists will always give a sort of qualified answer. You know, they will say, well, it's 95% sure that there is climate change which is caused by man-made activity, or whatever. So then this leaves it open for somebody who doesn't want to believe in climate change because they work for an oil company, let's say, to say, well, then it's not certain. It could be that there's really no impact of man-made activity on climate change. And you can't answer that as a scientist directly unless you say, well, fine, but if you were told that 95% of the people who thought about the question thought one thing and 5% thought another, which side would you bet on? If you were a gambler, which side would you go for? Or putting it another way, let's suppose you think it's fine to pump out a great deal more carbon dioxide into the atmosphere. If you think that science doesn't really know what would happen because you don't think the models of climate change are good enough, would you do it anyway, given that you don't know what's going to happen? Or would you refrain from doing it on the grounds that it's too dangerous if you don't know what's going to happen? I mean, these are the sorts of issues you get all the time. You know, in Britain there was a big scare about the vaccine against mumps, rubella and measles, where it was claimed it was related to autism. This was false data, but people still believe it, and it had a big impact in that quite a few people died in a measles epidemic in South Wales a couple of years ago, because the vaccination of that area had been too low. So the danger in the public press of talking about what scientists believe and allowing room for what somebody else believes, rather than thinking about what the majority of scientists say, and, you know, trying, we have public media which are supposed to produce balance in their accounts. If they really produced a balance by producing 90, let's suppose it's 95%, producing 19 scientists who take one view every time they put on one who takes the other view, that would be a true balance of what is thought, but it's not what the media are going to do. Okay, I think I'll draw to a close. I just want to make a remark about the use of philosophy in cosmology. It seems to me one of the things Bernard didn't talk about is the way in which philosophy has affected views of cosmology. I'm sure that this played a part in the steady state versus Big Bang debate, that people took sides not based on what they thought about the evidence, but on their metaphysical viewpoints. I've never forgotten being at a conference at the Royal Observatory at which Guy Pooley presented the Ryle and Pooley data on radio source counts. Admittedly, we know now that that wasn't entirely accurate, but Hoyle stood up and immediately said, this is good evidence for the steady state, which it obviously wasn't. So, you know, if you're thinking about basing your physics on a predetermined philosophical view, well, I'd advise you against. First of all, if your philosophy is sound, that will be unnecessary. And if your philosophy is not sound, then you'd better avoid it anyway. I remember the question about uniqueness of the universe, although Sharma once said, paraphrasing Orwell, that a good cosmological theory would be one in which everything which is not forbidden is compulsory. That's clearly, for reasons that Bernard and John have explained, no longer the way we think about things. So I just want to finish. I've talked about various kinds of bound on what we could do in principle, what we can do in practice. I just want to frighten you all by reminding you of our ignorance, what we don't know. We don't know what the right theory of quantum gravity is. We don't know what any of the inflaton, the dark matter, and the dark energy are. We don't know why the initial state that seems to give the correct answers from inflation, the initial quantum state, should be the one that's usually assumed. We don't know really how the quantum classical transition works. And we don't even know what the meaning of quantum theory is. I mean, there's these big debates between many worlds. So I think whether or not these are bounds in the sense that we will never go beyond them, limits in the sense that Bernard described that we should think about breaking, they certainly are bounds on what physicists and cosmologists can currently do, and they may, insofar as they can be broken, be bounds which we have to rely on those in the room younger than me to resolve. So I'll stop there.
Thank you very much. So we have short time for questions. Please.
You raised again this very sort of interesting point about falsification and testing and so on. And you know, I was fairly anti-Popper as well. I think the key sort of weakness in the sort of emphasis on falsification and testability is that, you know, is the presumption that an experiment that appears to rule something out is correct. And that's simply not the case, necessarily, from some of the examples you've given and that we know in the history of fundamental physics. And I think what you do instead is that, say, all you can do with a theory is change the likelihood that it's true or false. You can never rule it out completely, and you can never rule it in. And this Bayesian point of view, I think, is a better picture of what we do in practice. I mean, sometimes the evidence makes the likelihood so high that we regard it as essentially true for all practical purposes. But, you know, what lambda CDM might be ruled out next week by some observation that we haven't thought of, or we might discover that some of the observations that we think are supporting it weren't correct. So we have to have a philosophy of methodology which, you know, can allow for that situation. And I think Popper doesn't. It assumes that all experiments are definite and correct and actually falsify things or not. But that clearly isn't the case.
Yes, I think that's right. It's clearly too absolute. I mean, it quite properly directs our attention to an aspect of science which tends to be honoured more in word than in deed, namely the need to change our theory in the light of experiment. You know, people are very reluctant to change, as Bernard mentioned. But there are, I mean, another possibility, for example, is suppose that all potentially falsifying observations have been made. You can't think of anything more that you could do. Would that mean that the theory you had was then unscientific? or would it become unchallengeably true? Neither of those options is very attractive. What I do find interesting is I have a manuscript of Joseph Sierczynski, whose name was mentioned earlier, later the Archbishop of Lublin, in which he talks about replacing falsification as an idea in cosmology with what he calls disconfirmation. So something which is not consistent with the theory, but doesn't show that it's false. I mean, maybe that would be the sort of thing that, you know, the period when inflation had to accommodate a believed density of about 10% of the critical density, that 10% could have been a disconfirmation of the standard way of doing inflation. It's not falsifying. So maybe that's what we need to do, is develop a theory which is in a sense a sort of, it's another way of saying what you've been saying about a Bayesian approach and not being as absolutist as Popper.
Any more questions? Yes.
I was interested, Malcolm, in the remark you made about George Ellis's view that, you know, you can't, just because you can't predict something because it's non-computable doesn't necessarily mean you have to give up reductionism. But I'm not really quite certain I don't think it's just the non-computability which is the problem. I mean, the problem is that there are certain things, like in quantum mechanics, the whole point of quantum mechanics is it's unpredictable, not just because of lack of information. There is an intrinsic randomness. And I would say, for example, that the interaction of consciousness is an example of something which is intrinsically not just non-computable, but is random. So I'm a little bit more in sympathy with George, because I don't think it's just a matter of non-computability.
Well, that touches on, I mean, that sounds a bit like Roger Penrose's ideas about consciousness coming in some sense from quantum mechanical unpredictability. On the other hand, I think since we don't understand what quantum mechanics really means, I think I'm a little sort of hesitant about asserting firmly that it's intrinsically random, because we don't know how to interpret quantum mechanics. We can do the sums, and we get very good answers that work for all sorts of occasions, but we don't know what they mean. At least I don't know what they mean.
I thought it was always assumed now it wasn't just a matter of not knowing what the system was, that the system wasn't a concept. I thought that's the aspect of experiment.
But I'm not sure you have to go to quantum mechanics to do that. I mean, it's clear that, you know, there isn't just one star, and they differ. There must be some random element that affects them, whether you think of it coming from quantum mechanics or not.
More questions? So maybe I ask one question. Science and physics especially consist in formulating physical laws and principles. This means that there is some general behavior of many objects. We have many objects and one law. But in cosmology we have only one object. How we can distinguish between object and the law? If we try to think about Maxwell equations in the same way as we think about the universe, we may have the same problems of the same kind.
Yes, it's interesting that. I mean, I think one could attack that from a different direction, which is to ask, I mean, suppose you only can do, I mean, you can't build 100 large hadronic colliders. You rely on the results from one. So is there a bound to the number of experiments you have to do before you accept it as a good theory, if you reject cosmology on the grounds of the existence of only one universe? You know, if you say, well, all right, science is fine providing you can do at least 100 different examples. Why 100? Why should it be any better to do 100 than do one? So it's not clear to me that cosmology is different from other forms of science in that respect. All right, it's only got one, but almost any science has only a finite number of tests. It may be a large number, but it's only a finite number. And as a mathematician, you know, once I get 2, It's sort of 1, 2, many, many, many. You know?
If there are not questions, so thank you very much again.